I want to introduce Dr. Chao a little bit. Dr. Chao Wu is a reader in the Department of Civil and Environmental Engineering at the Imperial College of London, where he also served as a PhD supervisor, a member of the Departmental Academic Committee, a missions of the officer for the MSc program, and executive director of the Imperial Hydrogen Research Center. He received his Bachelor Engineering and Master Engineering degrees from Tongji University and his PhD from Monash University. Before joining Imperial, he held research and academic positions at the University of Michigan, EPFL, Nanyang Technology University, and Beihang University. His research focused on fiber-reinforced composites and energy infrastructure, with a particular interest in next-generation composite technologies for hydrogen storage and transportation, geothermal energy applications, and wind turbine blade recycling. He has led multiple research projects funded by the National Natural Science Foundation of China and is currently the principal investigator of a UKI Future Leaders Fellowship. Dr. Wu has published over 150 SCI Index journal papers. He also served as associate editor of several SCI journals, including the Journal of Composites for Construction, and is an executive committee member of the International Institute of FRP in Construction, which is named IIFC. So now let's give a quick applause to Professor Chao.
Okay, thank you, Professor Xian, for your kind introduction, and thank you very much, Professor Dai, for your invitation. And it's my pleasure to be here at CTU and share some of my research on fiber-reinforced polymer composites in civil engineering constructions. So firstly, a little bit of introduction about the material. Fiber-reinforced polymer composite, definitely there are three key components in the material. Firstly, we have continuous fibers, which is embedded in the polymer resin matrix. Okay, and also there is an interface between fiber and matrix. So there are three key components, and this material is very versatile because we can use different fibers, different polymer matrix for manufacturing of this particular material. And as you can see, we can use carbon fiber, glass fiber, aramid, and even natural fiber in FRP. And also we have different polymers like polyester, epoxy, polyurethane. So it's very versatile. And however, there are some disadvantages we have to be careful about when we are using this material in civil engineering construction. Firstly, the cost. So we are always challenged by industrial people asking about the cost. And also it is a linear elastic material. Normally it's brittle. It fractures in a brittle manner, which is very different from ductile material like steel. And also because we use polymer, it's a temperature sensitive material. So when you are using it in building constructions, we have to consider the fire design. Just one example showing the benefit of using FRP in construction. From a civil engineering background, so we all know how to design a bridge using concrete. So if you build a concrete bridge 13 meters long, normally it will be 30 tons in weight. If you use FRP for the construction of the same bridge, normally it's only 2 tons. There is a photo showing a full-scale pedestrian bridge, which I designed and fabricated in Beihang University. It's 13 meters long, 2 meters wide. The weight is only 2 tons. As you can see, this is a good example of the lightweight nature of this material. FRP, because of its versatile nature, so it has been used a lot in different industries like sport. We are playing tennis using carbon fiber rackets. We are taking flights like Boeing 787, 80% in volume of the airplane is made of FRP composite. And also now China is promoting wind energy, and wind turbine blades, they are normally made by glass fiber composite material. And in automobile industry, we are driving EV cars now. So reducing the self weight of the car is very important because we can save the battery life. Currently they are using a lot of glass fiber composites in the car body. We are civil engineers, so I'm more interested in using this material in civil engineering constructions. So several examples of using this material in civil. So this is a footbridge in the UK, which was constructed in 1992. It was the longest bridge at that time. It's fully constructed using FRP composite. This is another bridge which was constructed recently in 2023. That was designed by Network Rail in the UK because they favor this material because there are a lot of trains running every day. They don't want to interrupt the operation of the trains. So they use prefabricated FRP components so they can construct the bridge overnight. So the benefit is fast construction. This is another bridge, Avasson Bridge in Switzerland, which was constructed 2012. This is a traffic bridge, so like we can so the cars can run on the bridge. Initially it was a concrete bridge, and because they wanted to upgrade this bridge and they want to do it faster, so they chose to use FRP wrapping balsa wood as the deck, and so they can complete the construction in one day. This is another interesting building in Switzerland. As you can see, a roof structure is supported on glass facade. And glass is not very strong. So in order to achieve this architecture design, they require a very lightweight roof structure. They don't have any other options but using FRP because, as you can see in the second photo here, they wrap a foam with glass fiber fabrics, and so they use that kind of composite structure for the roof. And you must be very familiar with this structure. It's Apple Steve Jobs Theater. So I'm expecting the iPhone Ultra, which is going to be introduced in the coming September. So probably you will see the promotion in this theater here. As you can see, they use the same concept. They want to have a very transparent architectural design. They want to use all facade for the building, and because of that, they don't have other options but using all FRP roof structure because of its lightweight characteristics. This is Art Science Museum in Singapore, and you see this elegant design. It's like a flower. They use FRP in the facade. The reason was that they want to achieve a very curved, beautiful, and architectural design without any joints. So FRP can be manufactured flexibly. So that's why they use this material. And also Singapore, the weather there is very similar to Hong Kong. It's a humid, very warm. It's close to the marine environment. So corrosion is a problem. So that's why they choose using this material for durability purpose. This is another bridge in Beijing, which is called Qianhe Xielu Bridge. As you can see, this bridge was designed, has a curved design. It looks beautiful. So the external cladding architecture is achieved using FRP composite material. And actually, the load supporting structure is a steel truss bridge, which is inside the architecture. So the external architecture is used to protect the inside, the steel bridge inside. So as you can see from this slide, FRP we can make it into different products. For civil engineering applications, we have prefabricated strips, we have dry fabrics, we can have FRP bars. We also have different FRP sections of different shapes. We can have tubes, cables, and panels. As you can see, we can use it in many different applications in civil engineering. So in my opinion, in the civil engineering applications, there are two directions using this material. One is we can use FRP for existing structures, so we can rehabilitate old structures, restore the capacity. In the first photo, you can see that a technician is wrapping concrete bridge using FRP fabric. It's a very common practice nowadays because we have the design standard available for this kind of practice. And the second image is of all FRP office building, which is in Switzerland. So that building was constructed mainly for demonstration purpose. That showcase we can use this material actually for the real office building. It's 5-story building. It looks beautiful. So next, I'm going to briefly introduce some of my research in these two directions. One is for existing structures. If I have time, I will also quickly go through some research for all FRP constructions. And finally, I will introduce some of my ongoing research at Imperial College London. Firstly, the existing structures. This is the Westgate Bridge in Melbourne, Australia. So this bridge consists two parts. First, it's a long span cable stayed bridge, and also it has a approaching bridge, which is made by concrete. So the main span is made by steel box girder. And maybe 20 years ago, the government decided to increase the traffic on the bridge because of the traffic jam problem. Because they want to increase the traffic, the live load acting on the bridge increased. So they want to accordingly increase the capacity. So for the approaching concrete bridge, they used a lot of carbon fiber composite material for the strengthening purpose. However, for the main span, they use conventional strengthening methods like welding steel plates, bolting steel stiffeners. So why they didn't use the same material for steel bridge? Because at that time they didn't have any standard to follow for the design for the application. In order to address the research gap, so my research was about how to strengthen steel structures using carbon fiber composite material. And we did, and our focus was on fatigue performance because in steel structures, we have two challenges. One is fatigue, the other is buckling. So we have a lot of seam vault steel structures, right? It's very different from concrete structures. So in order to explore how to use FRP in steel structures, we address the first challenge in increasing the fatigue performance using carbon fiber composite material. So we did a lot of fatigue testing. So you see, this is a very simple steel plate. And in the center, we have a prefabricated crack in the center. And also before bonding FRP on the surface, we have to carefully treat the surface well for better bonding, increase the bonding quality. So we used sandblasting. As you can see, the surface is cleaned. And we use epoxy to bond the two material together. We attach FRP on the steel plate with different configurations because we want to investigate how the bonding length, how the bonding width, how the location of FRP material affect the performance of steel plate, right? And in the fatigue test, we want to get this crack propagation curve. As you can see, the vertical axis is the crack length. The horizontal axis is the fatigue cycles. So this is called a fatigue crack propagation curve. However, because the surface of steel plate is attached with FRP laminate, so you cannot see the propagation of the crack, right? You cannot see it. It's covered by this FRP material. So we used a technology which is called beach marking technology. So this is the fatigue cycles. So we use a greater, larger stress range. After a number of cycles, we reduce the stress range, and we repeat this loading pattern, right? Why we did it? Why we did it? Because this is the Paris law. Paris law is a semi empirical model which can describe the crack propagation behavior. So, according to the Paris law, if you change the stress range, which is delta sigma, so you will change the stress intensity factor at the crack tip, and you will change the crack uh, propagation rate, the speed of crack propagation. So if you slow down the crack propagation, it will create a mark on the fracture surface. So this is the fracture surface after fatigue testing. You can see we created a lot of striations on the surface. So by measuring these striations, so you can plot this crack propagation curve. So this is the testing results. So as you can see, for the steel plates without FRP strengthening, we can find out the fatigue life. All right. So this is the crack length at failure, and this is the corresponding fatigue life. And the other curves correspond to samples, specimens with different strengthening configurations. As you can see, it's very effective. We can increase the fatigue life. Effectively, we can increase fatigue life by 7 times. So this is the specimen that we get the best result. So the width of the steel plate is 15 centimeters. And if we use a 10 centimeters wide FRP covering the center crack, we can increase the fatigue life by 7 times. If you cover the whole surface of the steel plate, we can achieve an infinite fatigue life. That means the specimen doesn't fail after 2 million cycles. So the testing result only tells us that FRP is very effective in terms of increasing the fatigue performance. However, if you tell the designer, engineers, they will ask you, okay, it's a very nice material. If I use it on steel structures, can I know the fatigue life? Because if you don't know when the structure fails, you will never use the material because it's too dangerous, right? So you know it's effective, but you never know when it fails. Then no engineers will use it. You will use this material. So the next, even more challenging question is how do you predict the fatigue life of steel structures, which is strengthened by IFRP composite material? And then we come back to the Paris law. As I mentioned, Paris law can describe the crack propagation of steel structures with under fatigue loading. So if you open any steel structure design code, design standard, you will always find this formula. So that means you can predict for any steel structures, for typical steel structures details, you can always predict the fatigue life using Paris law. So for example, for a steel plate with a through thickness crack in the center, you have a remote loading, uniform distributed along the edge, which is perpendicular to the crack. Then there is a theoretical solution for the stress intensity factor at the crack tip. So this is the formula given in the design standard. So you know the stress intensity factor. So you substitute delta K in the Paris law. Then you do integration, definitely from one crack length to another crack length, you can work out how many fatigue cycles you need, right? So then that means you can predict the fatigue life. However, if you cover the crack using FRP plate, you can imagine the stress field at the crack tip will be changed, will be very different from the pure steel plate. So that means this stress intensity factor does not apply anymore. So if you don't know the stress intensity factor, you couldn't use the Paris law to do the prediction, right? So then how can we predict the fatigue life? So we were inspired by the modification factors. Here, F for the theoretical stress intensity factor, there is a modification factor. Why do we need a modification factor? Because delta sigma times a square root of pi a, that is the delta K for an ideal steel plate, infinite large. And we need a lot of modifications. We need to modify this delta K considering the finite size geometry of the steel plate. We need to consider different stress distributions, different shape of the crack, right? So that's why in common steel design standards, they introduce a lot of modification factors. We were inspired by these modification factors. So we were thinking, how about we introduce additional modification factors? They can consider the contribution of the or effect of FRP plate. So this is how we did it. So firstly, it's very simple. Why FRP can improve the fatigue life? It's very simple because this is the section view of the steel sample with CFRP attached on both sides. So this is the remote stress range. Without FRP, the crack will carry this remote stress. And if you attach a layer of material, so that material will share the remote load. So that means the stress at the crack will be reduced. So if you have smaller stress, you definitely have a longer fatigue life. So the concept is very simple. If you can convert this FRP material into equivalent steel, so that means you increase the steel thickness, then you can calculate the stress, the new stress at the crack. Then you can use the classical steel design strategy, right? You can keep using the same steel design standard. So this is how we did it. So load sharing depends on the stiffness of two materials, right? So we convert the FRP material into equivalent steel. Then that means the steel thickness increases. So then we can calculate the new stress at the crack because of the load sharing mechanism. So then the new stress, the updated, the smaller stress is a fraction of the original stress. Then the fraction here is a modification factor. So this modification factor considers the stiffness effect of FRP. So this is the first modification factor we introduced that can consider the material properties of FRP. So that means in order to improve the fatigue behavior of steel plate, it's better to use a FRP plate with greater modulus, right, or thicker material. Another effect we have to consider is normally the FRP strengthening plate is smaller than your steel structure, right? You cannot cover, most of the time, you cannot cover the entire surface of the steel structure. You can only cover a finite size over the crack location. So that means the red curve represent the crack behavior underneath the FRP material. So under the CFRP strengthening material, so the crack will open underneath it. And because of the bridging effect, it will close at the tip. And it will propagate. And eventually, the crack tip will go out, right? Will go out of the area covered by the CFRP material. And it will open again, right? Because you don't have any material to bridge the crack edges. So when the crack propagates and it comes out of the covering area, how do you consider the dimension effect. So if you have infinite size of FRP, you don't have to consider this cracking behavior. If you have finite size, you have to consider the cracking behavior. So we don't have any theory, so we have to use some empirical calculations. So here, because we want to consider the effect of the size of the material, we introduce another modification factor. And we don't have any theory to derive explicitly the formula for this modification factor. However, instead, we use the stress intensity factor of the testing curve. So after fatigue test, you have this crack propagation curve. So using this crack propagation curve, using the Paris law, you can calculate the stress intensity factor of your sample, right? You do your fatigue test, you get the crack propagation curve, you can calculate the stress intensity factor at any crack length, right? So you can calculate the real stress intensity factor. And yeah, so the effect of CFRP geometry has already been included in this stress intensity factor. How can we isolate it out? So we divide the real intensity factor by the theoretical intensity factor of the steel plate only, right? So you can calculate the stress intensity factor of the steel plate without CFRP strengthening, right? So in this way, you can isolate the effect of CFRP geometry. So because we have a lot of experimental curves, so we can calculate the experimental stress intensity factor. And we can do this calculation, we can calculate the modification factor. So we have a lot of data points on this figure. So vertical axis is the modification factor, considering FRP geometry. Okay, and horizontal axis is a parameter that we introduced as non-dimensional parameter because we believe that the modification factor is a function of crack width, width of the CFRP and width of the steel plate, right? So we calculate a lot of data points using experimental curves. Then we do curve fitting. We do curve fitting. So this is the result of curve fitting. So it's a two-segment function. Okay. So as you can see, the modification factor here is determined by the experimental results. So if you do a lot of fatigue testing, you can get a more accurate result. So that means this formula will evolve, will become more accurate if we have more experimental data in the future, right? So in this way, so far, we have introduced two modification factors. One, it considers the stiffness, the material properties of CFRP. And the second modification factor considers the geometry of the material. Then we can introduce these two modification factors in the Paris law. So that means in the future, when you design steel structures strengthened by FRP, you can continue using the current available steel standards, right? So the stress intensity factor is available in the steel standards, steel design standards, and you only need two additional intensity factor modification factors for CFRP. Okay, so that's easier for civil engineers to design the structure. Another issue for strengthening is the galvanic corrosion, because we need CFRP, carbon fiber, for steel structures. And carbon fiber is more electric conductive than steel. So that means the electrons in steel is more easily go from steel to carbon fiber. So if the environment is humid and a lot of oxygen, you will see corrosion. So if the two materials contact in a corrosive environment, you will see galvanic corrosion. So something like this. So in practice, it is proposed that when you bond, before you bond carbon fiber on the steel plate, you introduce a layer of glass fiber fabric in the glue, in the adhesive, so that the glass fiber can separate the carbon fiber and steel plate. So they don't contact each other. So there is no issue of galvanic corrosion. However, nobody answers that if you introduce a layer of glass fiber, how it will affect the bond. Because bond is a critical linkage, right? If you don't have the bond, you don't have a strengthening effect. So we did a lot of static testing and fatigue testing, and this is the result. The blue curve is the result for specimens without glass fiber in the bond line, and the black curve is the samples with with a glass fiber in the bond line. So for static loading, our conclusion is that okay, you can use a glass fabric to avoid galvanic corrosion. It's good for your static behavior, right? You see improvement in static strength. However, if you do fatigue testing, the interface will be negatively affected. So from the fatigue results, so the shaded bar represent the fatigue life of the interface without glass fiber. And if you use a layer of glass fiber, the fatigue life even drop by half. So that means in bridges, in structures like bridges, which is sensitive to fatigue loading, it's not recommended to use glass fiber to avoid galvanic corrosion, right? Because it introduces defects in the bond line. So fatigue is very sensitive to defects. So if you have defects, you have lower fatigue behavior. And our recommendation is that for applications without any fatigue issue, it's okay to use glass fabric to avoid galvanic corrosion. But for fatigue applications, it's better not using glass fabric. Instead, you have to carefully treat the bonding surface before you bond carbon fiber on the surface, because all you need is to avoid the contact between carbon fiber and steel. So if you already have a layer of glue, the glue, if you do it properly, can separate the two materials, right? And also, we focus a lot on the interface. If you want to use this material for structure strengthening or repair, you always have technicians on site. You install the material on the surface, you brush the surface using glue, then you attach the material on the surface. And you cannot promise 100% good quality of your installation, right? You always introduce defects to the bond line. For example, you may have some porosity, so your air voids in the glue, and you may have kissing bond. You may have some enclosures, all right? So some micro cracks. So the bond line is never perfect. However, in the literature, we have a lot of models, theoretical models available to calculate the interface capacity, all right? Like Hart-Smith model, and also Professor Teng in PolyU, they also have their own model to calculate the interface strength. That's theoretical prediction. They never consider the voids, the defects in the bond line. And so our question is, you have the theoretical capacity, but what if there are defects in the bond line? How much reduction we have to apply to the theoretical solution? So in order to answer that question, we did a lot of experimental testing, finite element analysis. We introduced defects of different sizes, different shapes at different locations. We did a lot of analysis. And here is one of the results. It's very interesting. So the vertical axis is the interface capacity, loading capacity. The horizontal axis is the size of the defect in the bond line. It's very simple. the larger the defect you have, the smaller the capacity of the bond line, right? It's very simple. You don't have to do any test. We know that. But the interesting result is that if you look at these two curves, the black curve is the strength reduction because of a single defect in the bond line. And the red curve is the strength reduction because of the multiple defects. So that means in the bond line, if you have multiple defects of the same size as the single defect, you have greater reduction. So that's a bad news for this technology. Normally, it's very difficult to detect very small defects using NDT method, non-destructive testing method. So if you have a lot of small defects which cannot be detected, and you think it is a perfect bond, but you have a lot of reduction in the practice, you will be very unsafe for this kind of application. So our work is to answer how much reduction we need when we have multiple small defects. And here is our solution. So the vertical axis is the reduction factor we need to apply to the theoretical prediction. The horizontal axis is the size of the defect. And we have two boundaries. So definitely, if you have larger defect, you have greater reduction, right? So the lower boundary here is a reduction factor for a single defect. So the upper boundary is the reduction factor for multiple defects. And so the data points in between these two boundaries, they are results from a mixing of different defects, different size, different shape. So that means you don't need to care about the shape of the defect. You don't have to care about the mixture of different sizes, different shapes. You only need to work out the upper boundary. That's it. So that's the maximum reduction of the bond line when you have a defect. So we did some curve fitting. So the lower boundary, this is the simple formula. For the upper boundary, so that means you calculate the lower bound, then you add 7% reduction, additional reduction on top of the single defect reduction factor. Then we develop a design procedure for FRP strengthening steel structures, considering the interface defect. So in practice, after you install the material on site, you always do NDT testing. You want to identify some defect, check the quality of the bond. So if you can detect defect, then you need to ask yourself, is it a single defect or multiple defect? Or if you have multiple defect, you follow the flow line. Okay, so you can use this model to work out the reduction factor. So this procedure can be coded. You can use MATLAB or Python to have a automatic calculation. You don't have to do it manually, right? So what you need to do is you work out the theoretical capacity of the interface. Then you go to the site, use NDT, check the defects. Then you input the defect size to this coding, to this procedure. You work out the reduction factor. Okay, so I will quickly go through the new constructions. You know, in civil engineering construction, we require a lot of material. So the cost is very important for civil engineering. Previously, we didn't use FRP widely because it's too expensive. However, now we have the power extrusion technology. So this is power extrusion technology. It can produce material continuously at low cost. So this is a very interesting manufacturing procedure. So you can see we have continuous fibers that will go through the resin bus and go through the die, and it will give you the shape of your element. And you cure your resin, and you pull it out of the die, and you cut it into a specific length. So you can have elements of different section shapes. right? It's very similar to steel members, steel elements. However, because of this particular production manufacturing process, most of the fibers are aligned in the pultrusion process. So you can imagine that this material has a very good property along the fiber's direction, right? However, in the transverse direction, it's very weak because it's mainly resin resisting the load. If you want to use this material in civil engineering, unfortunately, our civil engineering structures, the stress is always three-dimensional. So that means you never have a loading that is mainly in one direction. In some cases, we have that kind of loading condition, but most of the time, like connections, it's very complicated stress state. So you always have stress, particularly to the fiber direction. So when we had this material, researchers in civil engineering were very happy. So they want to replace steel elements using FRP. However, when they did mm, uh, uh, structural testing, they noticed some premature failure at the cross section of the material. Because, for example, if you want to test a beam, the load is perpendicular, transverse to the fiber direction, right? So they never achieve the material capacity before the premature failure. So this is called, I call it web crippling. And this phenomenon is very common, well understood in steel structures. So if you open any design standards of code-formed steel structures, you always have this one chapter describing the loading in the transverse direction, which is called web crippling. And in those steel design standards, you always have formulas to calculate the capacity. However, in different countries, they publish design specifications for FRP structures. They don't have this chapter. They never describe how the material fails, when it fails, at what capacity. They don't have that chapter, although it's a very important loading scenario. So, so I did quite a lot of testing for web crippling. I want to find out a theoretical solution to describe this kind of failure. So, for example, this is a square rectangular section pultruded tube. So I apply the load in the perpendicular to the transverse direction. Different loading locations, different setup. And as you can see, this the photo on the right is the metal tube, right? So this is a FRP tube. Both of them under transverse loading, they fail completely different in a different way. Because metal is ductile, you never see the separation of fracture between the web and flange, right? You see buckling, you see yielding, right? Um, However, um, FRP is a linear elastic material. Um, so you see fractures. You see fractures. So the fractures normally happen at the web flange junction. And also you see fractures in the webs. So they have very different failure mechanisms. And uh, in addition to the closed rectangular section, I also tested some open sections like channel section, build-up section. So this is a build-up section of two channel sections. I want to make a larger beam element. So as you can see, they all fail at the web flange junction if you load it in the transverse direction. So in order to figure out the mechanism, we use DIC, digital image correlation technology. You use two cameras and monitor the deformation of the material under loading. You have this technology, I believe. So you can work out the strain distribution on the surface of the material under loading. And so this is the loading area on top of the flange. And as you can see, so this is the stress strain contour on the web surface. So the blue area, that means the material is not engaged in load carrying mechanism. So most of the load is only transferred in a limited area. So that means only a certain amount of material is carrying the load. Most of the other material is not working at all. So we extract the stress distribution along the web flange junction and we plot it, and it looks like this. It's a parabolic function, right? So this is the loading plate on top of the flange. And actually the stress is only distributed within a certain length underneath the loading plate. So the load stress distribution is like parabolic function. So because the failure happens at web flange junction, all you need to do is to do integration of the stress along the fracture surface, right? So this is the load. You do stress integration along the fracture surface, then you get the fracture load at the web flange junction, okay? So, and also, if your web flange junction is strong enough, it doesn't fail, then the load will be transferred to the web. So the web will carry the load. And so the stress will be transferred continuously to the web. So it is carried by a limited length of the element, right? So in that case, a thin plate is carrying the load. The plate will buckle, right? So you can work out the buckling capacity of the web in this shape, right? So this is the buckling capacity. Now you have two capacities. One is the capacity at the web flange junction, and another is the buckling capacity of the web. Then you compare these two capacities. If the web flange junction is weaker, it has a smaller capacity, then the element will fail at the web flange junction. If the buckling capacity is smaller, then it will fail by buckling, web buckling. So in this way, we propose the design formula for FRP material under transverse loading. And also for FRP construction, you always have to consider connections and have to connect different elements together to form a structure. And for the current practice, the bolted connection is very popular, although we know that bonded connection is more reliable. It's much better for pultruded material because for bolted connection, you have to drill holes, right? When you drill holes, you will break the continuous fibers, which is not good for pultruded material. Unfortunately, because we don't have a reliable NDT method, we cannot tell the bond quality. If you want to connect different elements using bonding, firstly, you have to make sure you have a reliable bond. But unfortunately, we don't have that technology to check the bond quality. So most of the applications, we use bolted connection. So we can disassemble it, and we can check the quality, right? Much easier. And so I did quite a lot of static fatigue testing of bolted connections and also connections under different temperatures. And we have theoretical model to predict the connection, the capacity of the connection under different temperatures. Because of time, I will not go into more details, but you can find out from this publication. And also in timber structures, in conventional timber structures, we use steel plates for connections. However, timber has a moisture in it. And with time, especially in humid environment, the steel plates will be corroded. And it's very difficult to replace steel plates in timber connections. So we propose using FRP plates for timber connections. And the design of the bolted connection will be totally different from steel connections. So we did some research on the bolted connection of timber structures as well. And here, I want to highlight this research, which is creep of FRP, because FRP has resin matrix in it. And polymer resin is very sensitive to creep. So that means under loading, it will deform slowly, and eventually it will fracture even under a stress much smaller than the material strength. So this is a typical creep behavior. So vertical axis is strain and horizontal is time. So with time, it will show three stages strain evolution. So firstly, the strain will increase and the rate, the speed will slow down, and it will enter the second stage. The creep rate will become constant, and eventually it will enter the third stage. So the evolution of the string is unstable, and eventually it will fracture. Although that stress may be much smaller than the material strength. And this is the strain rate under creep loading. So at the moment in the literature, there are different models to describe the creep behavior. And we have models which can tell at what time the material will fail under creep loading. And also we have models which can describe the creep rate in the second stage. However, there is no model available which can tell the time for the three stages, like when it enters the second stage, when it enters the third stage. There's no model to predict those those time. So our idea is that in civil engineering, if you only predict the failure time at that moment, it's very dangerous. Imagine you have a cable stayed bridge. The cable is made of FRP material, and you can predict when the cable fractures, right? So that prediction is based on a constant stress, right? You have a constant stress, you know when it fails. However, in a cable stayed bridge, the stress always changes in the structure. When you have a very heavy truck running on the bridge, greater than your design stress, it will fail much earlier, right? It's very dangerous. So we propose that the failure time should be defined at the end of the second stage. So we gave it some tolerance here. Unfortunately, we don't have any model that can predict the time there, right? The end of the second stage. So we, based on the molecular behavior of polymer material, we developed a theoretical model that can describe the full three stages of polymer material under creep. So this is expressed as a strain rate. And we have a lot of material constants to be fitted using experimental results, but it's much reliable, much easier than the available models in the literature. So this is the process for fitting the material constants in our model. It looks very complex. However, you can again you can use coding to make it a coding package. You don't have to do the calculation manually. Then you just need to do a very simple sample creep testing. Then you input the testing results in the coding package. Then it will work out the material constants, right? Then you can use that model to predict any stress, predict the creep behavior of the material at any stress. I also did some research on ECC, but I don't have time to go through it. So finally, my current research at Imperial, durability. Durability is very important for different materials, concrete, FRP, right? But I don't believe, we have a lot of researchers, they are doing accelerated testing in the lab under different environments. But I don't think we can come up with a theoretical solution that can give us that can predict the durability of any material, because the durability is so complex because it depends not only on the material itself, but a lot of different environmental conditions. So we are using machine learning. I believe machine learning has this capacity. It's good at finding an underlying pattern of a very complex database. We have collected, I think, the largest database for FRP rebar, and we are training the machine learning models, and we are developing a platform for the durability prediction of FRP rebar. And we have the platform available, but it's not published yet. And hopefully by the end of this year, we will have this model online and everybody can use it. And also any researchers who are doing accelerated testing, they can upload their experimental data. So our database will keep growing and the prediction will keep increasing. The accuracy will improve with time. Another area I'm working on is hydrogen. Hydrogen is a green material, and China, Europe, UK, they are promoting hydrogen in their national strategies. And hydrogen cannot be stored safely and transport safely in metal infrastructure because there is something called hydrogen embrittlement. And I believe there is a lot of opportunities for FRP in this area. You can make hydrogen tanks. You can make hydrogen pipelines using FRP for hydrogen transportation and storage. And recycling. So if you look at the market, FRP market in the world, we only have 10% of carbon fiber composite, 90% actually glass fiber composites. So we are generating a lot more glass fiber waste than carbon fiber. However, glass fiber waste are not recycled properly at the moment. Like taking the wind turbine blades, for example, the blades are mostly made by glass fiber composite material, and currently there are no effective recycling solutions. So we are proposing recycling the blades into cementitious material or turning it into new composite products. So we are working on it now. Hopefully we can report the results in the future. A little bit about Imperial College. So we have a similar campus size to CTU. But it's located in the center of London. So you see, this is Queen's Tower. So that's the center of the campus. So from the left to the right, walking maybe 5 minutes, you finish the campus. Very small, but it's located in a very nice location in London. We have Royal Albert Hall. So our graduation ceremony will be there. It's very beautiful. And in the north, we have Hyde Park, which is a beautiful park. And we have Science Museum, Natural History Museum, Victoria Albert Museum. So we also have a lot of research collaborations with those institutions as well. So similar to CTU and any other civil engineering departments, we have 6 directions. So we have environmental engineering, fluid mechanics, geotechnics, material structures and transport. And we have, I think, over 60 academic staff at the moment. And I'm working in the material direction, and we have a material center. So we have a lot of facilities available for material characterization. We also have a composite center, which is a cross-department center. We have academics from different departments. We are collaborating on different projects in this center. And this is my research group, Composites for Energy Infrastructure at Imperial College London. If you scan this QR code, it will bring you to my group website. And with that, I would like to thank you for your attention, and I'm happy to answer any questions.